Let us start with a basic method of defining sound. Sound can be defined through its pitch, its timbre, and its loudness. All sound is vibration. A plucked string of a guitar vibrates and in turn sends ripples of vibrations through the air in the form of sound waves. This is the same process that happens within a synthesizer, except instead of the vibrations being caused in a physical sense, they are created electronically. The speed of these vibrations determines the pitch. If the vibrations are slow, then the pitch will be low, and vice versa. We refer to these vibrations as the frequency of a sound, and measure it in hertz. Timbre can be thought of as tone. It is the quality of sound separate from pitch that allows us to distinguish it from other sounds. Timbre is created by the harmonic content of the sound and how those harmonics are ordered, or sounded. A sound is made out of the fundamental frequency, or first order harmonic, and partials, or overtones, equivalent to 2, 3, 4 times the frequency of that fundamental. The fundamental is always the loudest, and the overtones get quieter in relation to their position in their order. We call this the harmonic series. Loudness is the perception of amplitude. Amplitude affects the sound in two ways. Firstly, it defines the timbre of the sound by establishing a relative level of the harmonics. This is how we create the different waveforms. Secondly, it has an effect on how the sound changes shape over time. For example, a note played on a violin can take almost a full second to reach maximum amplitude, whilst the peak amplitude of a piano will occur very quickly. This second quality we can control using envelopes and call the shape of a sound. If we turn our attention now to a subtractive synth, we can see that there are 6 main components. We have an oscillator, a filter, an amplifier, 2 envelopes, and an LFO. Oscillators are an electronic circuit that generates a constantly repeating waveform. These can be sine waves, triangle waves, pulse or square waves, sawtooth waves, or just white noise. Oscillators provide your synth with its primary sound source and can be thought of as the guitar string. Filters are circuits designed to block certain portions of a signal. They accomplish this by preventing all frequencies above or below a certain point from passing through the circuit. This is called the cutoff frequency. The resonance control sets the amplitude of the cutoff frequency through the use of a feedback circuit. This is similar to how Q works on EQ circuits. There are a few different sorts of filters you will see on synths. The most common is the low-pass filter, which lets every frequency below the cutoff pass through the circuit. You may see high-pass filters. These allow frequencies above the cutoff frequency through the circuit, and occasionally you'll find bandpass filters, which allow a range of frequencies around the cutoff that are within the bandwidth set by the resonance control. There are 2 envelopes on most synths, and they function in exactly the same way. The only difference is their application. One is used to control the volume, and the other one to control the filter cutoff. The most commonly seen envelope is the ADSR, which allows control over the attack, the decay, the sustain, and release portions of a sound. These help us to control the sound's loudness with more fidelity than just a gate or an on-off signal. To control the volume over time, we use an envelope alongside an amplifier. This is sometimes labelled as a VCA envelope. This is how we can shape the sound's amplitude. The VCF envelope is exactly the same principle, is an envelope plugged into a filter. In much the same way that the VCA envelope affects the amplitude over time, the VCF envelope works with the timbre over time. It does this by controlling the frequency at which the filter is set to cut off the signal, allowing the sound to change brightness in relation to its length. An LFO is technically the same as a VCO, or oscillator, apart from two features. It operates at a sub-audio level and is often used as a control source and not a sound source, while sub-oscillators are a type of LFO that can be used as a sound source and follow the same rules as a VCO, just at a lower range. The simplest and purest waveform is a sine wave. Most natural or acoustic sounds are relatively complex and contain many harmonics. The sine wave contains no harmonics. A sine wave only contains the fundamental. The fact that a sine wave is actually a single pure tone containing no harmonics makes it an important building block in synthesis. Of all the waveforms mentioned here, the easiest to generate electronically is a square wave. A square wave exists only in one of two states, high or low. In electrical terms, this is as simple as turning on and off a circuit. Do it quickly enough and you generate a frequency, which, when sent to a speaker, will be converted into an audible pitch. A square wave is made of only odd harmonics, that is, the third, the fifth, the seventh, and so on. A square wave has a characteristically hollow sound to it, very much like a clarinet. The triangle wave shares some things with both the sine and the square wave. Its shape is related to the sine, in that it has some of the smoothness of the wave, as well as an emphasis on the fundamental. But like the square wave, the triangle wave contains only the odd harmonics, although in a different order. The resultant sound is hollow, like the square wave, but maybe not as bright. The sawtooth wave, also known as a ramp wave, is rich in both even and odd harmonics. This gives it a bright and almost buzzy sound, and makes it especially valuable as a sound source. The importance of a sawtooth wave will become even more obvious when we discuss filters, mainly because there is so much harmonic material to filter from it. So we can modify these basic waveforms by using the LFO. By applying the LFO to various different modules, we can cause different effects. For example, to create vibrato, all we would need to do is modulate the pitch of our oscillator. So if we select a sine wave on our LFO, and we select a saw wave on our VCO, you can see how it changes over time. As we add the pitch modulation, we can increase the rate of vibrato. This is the same technique as moving your finger back and forward on a guitar fret. As the frequency that your finger moves is not as high as the string's oscillation, therefore causing a subtle periodic fluctuation in pitch. We can do the same thing with our filter. If we have a waveform and we bring the cutoff down, and we can modulate the point that that cutoff is. This is referred to as filter modulation and can be useful to create different effects over time regarding a sound's brightness. So I mentioned earlier how important the saw wave was in relation to a filter. And that's because you can shape other waveforms out of the saw wave. This is because the saw wave has so many harmonics that you can simply take away until you get the shape that you want. For example, let's make this saw wave into what resembles more like a triangle wave by simply applying a low pass filter. All of a sudden we've got something that resembles a slightly rounded but altogether triangle wave compared to the sawtooth. If we continue to take out frequencies until we get down to one or just two fundamentals, we can get what resembles a sine wave. So a quick recap. The oscillators generate a waveform. The filter changes the timbre. The filter envelope allows us to control how the timbre is shaped. The VCA and envelope control the volume of our sound and its shape. And then we can add movement in the form of modulation with our LFO.